necessary if you have on the external side of the tunnel where you don't have a lot of oxygen. Normal current readings can be difficult to evaluate. So what we do instead is that we use the principle where we can polarize, include current to our steel, and see how it reacts. If it reacts very easily to a polarization, it would have a very low corrosion rate or no corrosion. So generally we think the corrosion monitoring system is a good system, both to reduce the uncertainty, but also to look at possibilities for plant maintenance in your structures. We also have systems that work for post-installed sensors. This is more difficult than on new ones, because new ones you can cast them into concrete and they are in the actual situation. The big challenge with this it's the same principle basically. The challenge is that you have some nails that you include in your concrete, and that is to get contact between this nail and the parent concrete that you have here, because you don't want to alter your environments in this case. They can look like this. Oh, that was a bit too. They can look like this, small nails, where this part here is what is in the parent concrete, 1 centimeter. And this is a reference electrode with a counter electrode around it. And this is what it looks like placed on site in different levels, and with the counter electrode in the center there. Based on this, we evaluated what the threshold chloride concentration was for our structure, and the deviation. There was quite a high deviation in this. And I have to be very honest to say some of the sensors did not work. And that's some of them, the cabling. You saw this this nice mesh that we placed to protect the cabling. That's difficult if you have a hard winter, or if you have people fishing, they connect themselves to this. That you could not have foreseen. Based on these results, a cathodic protection system has been installed. And when doing so, we took out all of those nails and looked at the corrosion condition of these. These are pictures on 3 of those nails after they had been treated with inhibiting hydrochloric acid, so that we expose the steel without causing corrosion on those. And you can clearly see pitting corrosion on some of them. We found a fairly good correlation between the condition of the steel and the measurements that we had made. But the data, I have to stress this, is limited data, and we do have some uncertainty in this. It's a challenge on how many of these can you afford to install, for instance. But as with the other system, now we have possibilities of making automatic monitoring system. That would be a big step forward in reliability on these systems. Before deciding to do cathodic protection, we had a lot of dust samples on chloride during the service life of the structure. They were built in 1982 to 1985, and you can see we did the dust samples throughout the service life. And when you look down here, this is just the peer numbers. You can clearly see that the chloride concentration increases at the depth of reinforcement in the splash zone. Having a threshold level even at 0.065%, even with uncertainties as you have here, clearly a lot of these chloride concentration exceeds a threshold level. Those 2 bridges now have a cathodic prevention installation with sawn slots where an anode ribbon is placed in these slots. And you're more than welcome to interrupt or...
I'll ask a question. Did you try to correlate, Fick's laws type of predictions about chloride penetration versus your both, I guess, with the chloride measurements and also your potential?
Yes. Thank you for that question. It's very difficult when you have an existing structure to measure chloride profiles and estimate service life. We did that, And we also found a big variation, because you have, even though you have a homogeneous structure generally, you do have small variations in water cement ratio. But we did a lot of also detailed chloride profiles, and we have a very good knowledge on what the diffusion, average diffusion up until now is. And also where we could see that we have a chloride concentration exceeding the threshold.
So was it average worse than what the theory predicts, or was the performance better than what the theory predicts?
They performed a little worse than what we had hoped, but that has partly to do with the concrete composition. The concrete composition on a lot of those marine structures in Denmark are low sulfates, low alkali sulfate resistance cements. So they are very low in C3A content. So what we fear is that they do not bind chlorides to a high extent. They were designed because there was a big fear that there would be sulfate attack in a marine environment. They did not. Chlorides were not that popular in the very early 80s. That came a bit later. So they did not focus so much on chlorides. They focused on the sulfate. So, and they had fly ash in the concrete, and we know from petrographic analysis that it's a very limited amount of fly ash that went in there.
So would you recommend have a little bit more calcium aluminate in the cement?
Not necessarily, because we know that the chlorides are also bound by C2S and so on. It should be what we've talked about. You should look at how the concrete mix you have, how that performed. But it's a question on, you could go from a low sulfate reducing to a moderate sulfate solution. That could get you somewhere at least. And now we know that we are more afraid of chlorides than we are of sulfates.
The after the fact, where you go and drill a hole, put what you call your nails in there and the sensor system there, I know it depends on how bad the concrete is, but if you were to say, hey, I think I've got a problem, how long would a system like that have to operate before you could get a meaningful result?
We would normally expect the values to stabilize, so maybe a 4-week period. The challenge is that you would like to include them where you estimate you would have corrosion in a critical amount, or where you don't expect them, meaning in different depths, but also in different levels. We have another bridge which has been monitoring also with the POST system, and it was clear from that that we had a higher corrosion rate just about the tidal zone, even though the chloride concentration was lower. But
so you're in a 4 to 6 weeks period or something like that?
4 to 6 weeks you should be able to get
some
results.
or not?
Yes, but you then have annual variations. If you do that in the middle of the winter, you may feel very comfortable that you don't have the problem. So you should wait. And the worst conditions corrosion-wise we found in our place of the world is not necessarily the summer with a high temperature, but the autumn and spring where you have it combined with humidity. So the wise thing would be to measure it over a period of time, so you had a good basis for concluding. Yeah?
We repaired a wharf after the earthquake, and we had to extend new bars with old bars that were coming out of the old concrete that had some fluorides in it, and we were concerned about the corrosion developing, the ions being exchanged between the new and the old. So we put a piece of zinc in there, tied it to the rebar.
Yeah, Victor has this system that was developed some years ago with these small zinc. If I go back to just takes a little time before we get back there. Might be a bad idea this, because we have to go the other way again in a minute. I'm just trying to look for this principle sketch on traditional repair works.
But I was always concerned about the zinc, of course, sacrificing to protect the steel. And then what happens to the piece of zinc? Yeah,
that question we raised with Fosroc, who invented it in those days. Now Victor are the ones who sell them. Now this takes a long time. So it's where you take out this area, and then you have a binding wire, and you have this small tablet, or it's a sink, and then it has a high pH value mortar with lithium and so on in it. That is a small cathodic protection system that is designed to overcome exactly this problem. We did some studies for Fosroc some nearly 10 years ago, where on different structures we measured how much current they could actually give and what the chloride concentration was, and we also measured the performance of them. Based on that, we said that they cannot overcome everything. If you have a high chloride concentration, they would not be able to provide enough current, and at the same time it would be consumed faster. So I think they also have it now that the amount of chlorides you have left in your parent concrete should not exceed 0.1% by weight of concrete, something like this. And if it does that, it's an okay system, it works. And then you ask, what about the sink in there? They did tests themselves in England, where they found that it did not expand significantly, so it did not spawn, because that would be a concern to raise. So they work, but you have to know where to use them and to which extent. Yeah. And I'm sorry, now we have to go all the way back.
You can go with the mouse.
No. Yeah, but then I have to shut down the presentation?
No.
Ah!
One the right way.
Yes, you are.
You can
Now,
right
come,
click to-
take it easy.
Oh, don't want to go too far.
Yep.
Yeah, one back. And yeah, there. And some words on stray currents. Stray currents can be a concern where you have DC operated trains. I put alternating current in parentheses because they have a very small rectifying effect if your frequency is high enough. For practical purposes, we do not consider this. Having said that, they can have problems if you combine DC and AC. We leave that out for the time being. But DC operated trains, where your return currents from your train has to go back to the transformer station, if it goes in a path which is not intended, it can cause corrosion on its way. It can cause corrosion of any metal structures that are run in parallel to your structure, or at least which is in your area of field. This picture is a picture I took of segments in the Bucharest metro at least 12 years ago. They were making a new station, and they took out the old elements, and so it was an element churchyard they went to. They were heavily corroded, and I thought there must be chlorides in this because it was pitting corrosion. I took some concrete samples home with me. No chlorides, and it matched very well with that. They had they had rivers through the alignment and so on, but no chlorides there. We did measurements, and it was stray currents and stray current corrosion. Before going on to the next slides, stray currents can also be resulting from cathodic protection installations. They are also direct current installation. High voltage direct currents or welding operations. You have to think about how you ground your system in that case.
So in, older cities where you have congested, buried infrastructure, it's very difficult to know what's going on. Right?
It is very difficult to know, because one thing is the structure itself. If you are really unlucky, you affect also the structures, foundations, everything else in the area outside it. It's a big challenge on some of the old structures. The principle on these stray currents, if you have a voltage gradient, is that you have current which will be running perpendicular to these voltage line. Where the current enters your steel, think about this as a steel in an electrolyte. It could be concrete, it could be water, it could be anything, but something that can lead currents. Current will be picked up in one end. A steel has a very, very low resistance. It would, in many cases, if that resistance path is lower than the resistance path you have outside,